Batteries play an increasingly crucial role in our modern way of life. They power cell phones, electric vehicles, and potentially even airplanes. More specifically, electric vertical takeoff and landing aircraft. They can also serve in the most vital and delicate part of our body, powering a pacemaker. Among the various types, lithium-ion batteries are particularly promising due to several advantages. First, they are lightweight. Second, they have high energy density, among the highest of major battery technologies. Third, they are rechargeable, making them ideal for consumer electronics and EVs. Lastly, they are cost-effective. Large-scale energy storage systems for solar or wind farms can be constructed at a relatively lower cost. A lithium-ion battery consists of an anode, which acts as the negative electrode, and a cathode, which serves as the positive electrode. Between these electrodes lies a separator and electrolyte, with the entire structure sandwiched between positive and negative current collectors. In this system, the cathode and anode store lithium. The electrolyte carries positively charged ions moving from the anode to the cathode and vice versa. The separator allows positively charged ions to flow but blocks the flow of electrons inside the battery. The current collectors enable electrons to flow through to the powered device, like a cell phone or an EV. During battery discharging, imagine an electric vehicle running on battery power. Positively charged lithium ions flow through the separator from the anode to the cathode, while electrons flow from the negative to the positive current collector, creating a current in the opposite direction. Conversely, when the EV docks at a charging station and starts charging, the reverse process occurs. Positive ions flow from the cathode to the anode, causing electrons to flow to the negative current collector, creating a current in the opposite direction, which recharges the battery. Despite being an amazing energy storage medium, lithium-ion batteries degrade throughout charging and discharging cycles. The degradation process is measured by the state of health, short for SOH. SOH is the ratio of the maximum battery charge to its rated capacity. It is represented by this equation, where Qmax is the maximum charge and CR represents the rated capacity. Another important attribute is the state of charge, short for SOC, which is the ratio between the remaining charge and the maximum charge, represented by this equation, where Q is the current charge and Qmax is the maximum charge. This graph shows the degradation of the state of health of 3 batteries across cyclic charging and discharging. Since batteries degrade, they have a limited lifetime. According to industry standards, when the capacity reaches 80% of its initial value, the battery has reached the end of its lifetime. We use the term cycle life to represent the number of times a battery can be charged and discharged before reaching its end of life. For example, we can see from the graph that the orange battery has a cycle life of around 500 cycles, while the blue battery has a bit longer cycle life, around 800 cycles. Battery degradation is a surprisingly complex process that involves the interaction of large parameter space. Some of the major factors impacting battery degradation include material factors, where the battery materials experience chemical aging as the progression of time, environmental factors, such as the temperature and humidity that the battery is operating under, and the operation of the battery, such as charging and discharging profile or simply the usage habits of the user on the batteries. Predicting battery cycle life is of vital importance, yet it remains a challenging task due to the complex interactions within batteries that impact their performance and longevity. Accurate predictions can accelerate research by enabling scientists to rapidly screen and test a large domain of new materials or designs, reducing development timelines. For manufacturers, reliable cycle life estimates ensure quality assurance, allowing them to identify and eliminate defective units before they reach the market. Most importantly, for us consumers, precise life cycle forecasting enhances end-user safety by reducing the risk of sudden failures or hazardous conditions devices. All in all, accurate battery cycle life prediction helps us achieve more reliable medical devices, fewer charging stations for EVs, and longer-lasting phones. In the early days, first principle models are investigated by researchers to predict battery cycle life. This is considered a classic approach. First principle models simply mean that they are models based on fundamental physics laws or chemical processes. The first principle model-based battery cycle life prediction methods published earlier can be summarized into 4 categories. They are growth of the solid electrolyte interface, lithium plating, active material loss, and impedance increase. Due to the time limit, we will only summarize the first 2 types. The first one is growth of the solid electrolyte interface. Solid electrolyte interface is short for SEI. This is the structure of a lithium-ion battery that we are familiar with. As the battery undergoes the cycles of charge and discharge, SEI will form at the anode. There are 2 known facts for this modeling method. The first one is that the formation of SEI contributes to the capacity fate of the battery. Another one is that the formation rate depends on the temperature. Based on the known facts, we can develop 2 analytical models. The first model is a mapping between the amount of SEI formation and the capacity fate of the battery. And the second model uses the Arrhenius equation to fit the formation rate and the temperature. Battery cycle life can then be predicted with these 2 models, with temperature measurement being the only input to the model. Here is the workflow. Temperature is input into Model 2, which will predict and output the formation rate of SEI. Then plug in this formation rate to Model 1, and the capacity fading curve of the battery can be predicted. Notice we defined that the battery cycle life ends when the capacity is reduced to 80% of its rated value. So the final predicted cycle life can be found on this capacity fading curve. Lithium plating is another first principle battery cycle life predicting method. This is an example of a battery capacity fading curve. The curve can be divided into 2 regions. The first one is called linear region, where the capacity degrades slowly. The degradation in the region is mainly contributed by the SEI formation we just introduced. The second region, where the battery capacity degradation really starts to accelerate, is mainly contributed by lithium plating. This transition process can be summarized by the diagram below. This is a fresh battery cell. As the cell is charged and discharged, the SEI layer is formed and grows thicker, reducing the anode porosity. This process will induce localized lithium plating. At high cycle numbers, lithium plating will accumulate, which leads to localized pore clogging and sharp resistance rise. This is when the battery degradation really starts to take off. An analytical model can be established by considering SEI formation, lithium plating, and other related parameters to predict battery cycle life. First principle models often work well in theory, but real-world battery cycling conditions are far more complex. These models typically focus on just a few specific mechanisms. As a result, their predictions often fall short in practical applications. Since around 2015, the rapid advancements in machine learning, often broadly referred to as AI, have inspired scientists to apply these techniques to battery cycle life prediction. Machine learning models have demonstrated significant advantages over first principle approaches. First, they are designed to handle complex parameter spaces, where multiple variables interact in ways that are difficult to model explicitly. Second, while often described as a black box method, machine learning can uncover patterns and relationships in data without requiring predefined assumptions, revealing insights that are often unforeseen by human expertise. Finally, these models are particularly effective at accounting for individual battery inconsistencies, such as variations in manufacturing or differences in cycling conditions, making them highly adaptable to real-world applications. Early machine learning approaches often used long short-term memory, short for LSTM models, to predict the remaining useful life of batteries. While the detailed workings of LSTM are beyond the scope of this video, the key idea is straightforward. LSTM acts as a black box with memory cells and gates, taking time series data as input and forecasting future trends as output. This makes it well suited for capturing patterns in sequential data, such as battery performance over time. In a 2018 study published in IEE Transactions on Vehicular Technology, researchers used early battery capacity measurement data to train an LSTM model for predicting the remaining useful life, RUL, of batteries. Once trained, The model could be applied to new batteries through an online updating process, which eliminates the need to retrain the model from scratch. Instead, a shorter segment of new cycling data is used to update the model and achieve accurate RUL predictions. However, this approach has limitations. Online predictions still require several hundred cycles of data, typically after the battery has already begun degrading. The key challenge remains the lack of a sufficient volume of battery cycling data for more robust predictions. In 2019, a groundbreaking study titled Data-Driven Prediction of Battery Cycle Life Before Capacity Degradation was published in Nature Energy. This research was a collaboration between Professor William Chue from Stanford and Professor Richard D. Bratz from MIT. One of the main contributions of this work is the introduction of an open-sourced battery cycling dataset, the largest at the time, consisting of 124 commercial lithium-ion batteries tested under various fast-charging protocols. The batteries used in this study are from A123 systems, and testing is conducted using an Arbon LBT battery tester. A battery tester repeatedly charges and discharges the batteries, simulating real-world usage while monitoring key parameters such as capacity, efficiency, and degradation. To maintain consistent testing conditions, the setup is placed in an environmental chamber, keeping the temperature constant at 30 degrees Celsius. With the dataset in hand and using machine learning algorithms, this work demonstrated two key findings. First, by using only the first 100 cycles of capacity data, the battery cycle life could be predicted with 91% accuracy. Second, using just the first 5 cycles of capacity data, batteries could be classified into high and low cycle life categories with 85% accuracy. The workflow begins with feature extraction, where researchers identified a crucial feature: the differential discharge curve between cycle 10 and cycle 100, and computed its variance. The resulting value showed a strong positive correlation with cycle life, making it a reliable predictor. The next step involved training machine learning models using the selected features, with elastic net used for cycle life prediction and logistic regression for high-low cycle life classification. A key highlight of this work is that strong predictive performance was achieved using rather simple machine learning models. This figure presents the cycle life prediction outcomes, with each graph showing results based on different feature combinations. In each graph, the vertical axis represents the predicted cycle life, while the horizontal axis represents the observed cycle life. The diagonal line indicates perfect predictions, where the predicted values exactly match the observed ones, and deviations from this line represent errors. The results demonstrate that the model generally achieves good predictive performance, as most data points are concentrated along the perfect prediction line. The authors also discuss the rationalization of the model, seeking physical evidence or mechanisms that explain why the model's predictions are meaningful. This step is more of a community practice when AI is first applied to a new scientific field. However, due to time constraints, we will not delve into the details of this aspect. In summary, this work serves as a significant starting point for the widespread adoption of AI-based approaches in battery research, but challenges remain. For example, while 91% accuracy is promising, there is room for improvement. Another key question is whether cycle life prediction can be achieved using only a single cycle, which would minimize battery degradation during testing. Additionally, the charging protocols used may not fully represent real-world charging habits, and the dataset is limited to one battery type, making it relatively small and not inclusive. Since the publication of this study, many follow-up works have been conducted to refine and expand this approach. Furthermore, this research has inspired scientists in other disciplines to adopt data-driven methods to accelerate their own discoveries. If you're interested, you can easily find more information online.